Hello, and welcome to the second video of Section 4.3 on the fundamental theorem of calculus. Mathematicians do not throw around the word fundamental lightly. In this section, we connect integration and differentiation, which allows us to compute integrals without calculating limits of Riemann sums. In the first video of 4.3, we developed Part 1 of the fundamental theorem of calculus. Now we'll see that Part 2 is a consequence of Part 1. An antiderivative of a function f of x is the integral of f of t from any constant a to x. In Part 2, we apply this observation to solving definite integrals. In particular, we show that the integral of a continuous function f on a to b can be computed by finding the difference of an antiderivative big F on the interval a to b. How do we show this? From Part 1, since g prime of x equals f of x, g of x is an antiderivative of f of x. If big F is also an antiderivative of little f, then we know we can write big F as g plus a constant c. Taking x equal to a in the formula for g, we see that g of a equals 0. Now big F of b minus big F of a can be written as g of b plus c minus g of a plus c. Canceling the c's and using the fact that g of a equals 0, we have that big F of b minus big F of a equals g of b, which equals the integral from a to b of f of t dt. Altogether, we have Part 2 of the fundamental theorem. You may be surprised that an integral, which was defined by summing the area of an ever-growing number of rectangles, can be computed with 2 points on a function. This result depends heavily upon the integrating function being continuous. In most concrete examples, the velocity of an object is modeled as a continuous function. Therefore, in these cases, the antiderivative of the velocity function is the distance function, and the integral of the velocity from a to b is equal to the difference of the distance function on the interval a to b. Now that we've introduced Part 2 of the fundamental theorem, antiderivatives become fundamental to integration. I recommend rewatching the video on antiderivatives and studying the common antiderivative forms. For example, we can integrate the function x cubed plus sine of x from 0 to pi by first calculating the antiderivatives and using Part 2 of the fundamental theorem. In this case, the antiderivative is x to the 4th over 4 minus cosine of x, and Part 2 of the fundamental theorem says we just have to plug in pi and 0 and then take the difference. Thus, our solution is pi to the 4th over 4 plus 2. It's easy to miss, but in this example, an important step was skipped. However, disaster was averted by luck alone. Recall the hypothesis of the fundamental theorem. A function must be continuous on the whole interval over which we are integrating. For example, the function f of x equals 1 over x squared has only the discontinuity at x equals 0, and an antiderivative of 1 over x squared is negative 1 over x. We can use the fundamental theorem to integrate f as long as 0 does not lie between the boundaries. We can see that the integral between 1 and 2 of 1 over x squared is 1/2 using the fundamental theorem of calculus. But the integral between negative 1 and 1 cannot be attacked with the fundamental theorem. In Calculus 2, additional techniques will be introduced to deal with issues where the fundamental theorem fails to apply. You've seen the basics, now work towards mastery through practice and study.